Right, this lecture is all about move constructors. Now the idea with a move constructor is that resources owned by an R value are moved into the object being constructed. Right, so the resources owned by an R value are moved to an L value. Before we look at the definition of a move constructor, we'll revise a few topics that I explained in previous lectures and in previous lessons. That includes what temporary objects are, and then also the difference between L values and R values. Okay, because an understanding of that is important for the move constructor. Let's start with unnamed temporary objects. Here I have an integer myInt, and I initialize that to 2 plus 5, so in other words I assign 2 plus 5 to that, or the result of 2 plus 5. So let's just see what happens here when we execute this statement. Right, so we are going to evaluate 2 plus 5, and then we are going to store that result 7, or that value 7, in a temporary object in memory. Then we are going to assign the value 7 to myInt. Then we'll destroy that temporary object that holds the value 7. Something similar is going to happen for your user-defined types. Here we have an entity as an example. This could be a struct or a class. We construct entity 1 in the first statement, and then in the second statement, we construct a temporary object by doing entity, parentheses, and specifying an argument. So in this case, let's say 5. Okay, but it does exist in memory temporarily, so it does get constructed and so on, and eventually it gets destroyed again. Once constructed, we assign that to entity 1, and then following that statement, that temporary object is going to get destroyed again. So the move constructor will allow us to reallocate or steal the resources from the temporary object instead of copying those over. Okay, in that example, you'll use an assignment operator. If an entity has a member pointer that points to a dynamic object right on the heap, then you have to do a deep copy, where you have to deallocate memory, you have to allocate new memory and copy stuff around. That is in a regular copy constructor or regular copy assignment operator. And in some instances that can be inefficient, and doing this with a move constructor is more efficient because, again, resources are simply being reallocated. That's especially helpful in reducing the amount of dynamic objects that are created on the heap or destroyed on the heap. With some of the upcoming illustrations, this should become more clear to you, like what's going on and exactly why this is more efficient. Alright, a recap on R value references and the difference between that and an L value reference. So at the top here again we start with the L value reference. In that first statement, p is an L value. Right, we do int p and we assign 5 to that. P is now an L value. Then we do a reference to an integer that is referred to as an L value reference, and we can assign p to that. Now with an R value reference, that is going to reference R values or temporary objects. Okay, and this is what we are going to use for the move constructor. When used as formal parameters, the compiler will deduce which function to invoke based on the argument provided. Okay, only a slight difference here. We use 2 ampersands for the R value reference as opposed to 1 for the L value reference. And with the R value reference, we can assign a R value to that, such as 5 for example, or maybe some integer that we return by a value from a function. If you try and assign something like 100, so in other words an R value, to an L value reference, as you can see in the first statement, you'll get an error. But if you try and assign an R value to an R value reference, then that's fine, that will compile. On the other hand, if you try and assign an L value to an R value, again you'll get an error. Okay, I have this quick example in Visual Studio. I have this test function, okay, that is overloaded. So what is the goal with this example? The goal is simply to see what the output is going to be and what function, what version of this overloaded function is going to get called, depending on what we pass in. So the output statements here, I have L value reference. These output statements simply refer to the type of the formal parameter. It's important not to get the type of some variable confused with the category that it's in. So for example, here x is an R value reference, and then here in this formal parameter, x is an L value reference. That refers again to the type of the variable, in this case x, but in both cases x is an L value. X itself is going to be an L value. Okay, that is the value category. Why? Because it has a name and so it is addressable. So again, just a quick recap on that as well. Okay, now let's go back to main. I have this integer here called myInt, and I pass that into test. You can think for a second what is going to print out. Well, we've already run this actually, so of course it's going to run this L value reference here. Okay, L value reference. Okay, so I'm going to comment this out and you can see that we will get these red squigglies. An R value reference cannot be bound to an L value. If you build and run that, you'll get an error, okay? You cannot bind an L value to an R value reference. Alright, we'll actually come back to that one a bit later. I'll undo that. I'll uncomment this overloaded version here. Let's pass in an integer literal. I'll pass in 55. Now that is going to be an R value, of course. And let's see which one of these functions it will call now. And you can see we get the one where we have a formal parameter which has an R value reference type. This one right here gets prioritized. If we comment that out, this one will work fine because it is a reference to an integer constant. Okay, so that will actually work fine, L value reference. If we try and remove this now, this will not work. You cannot bind an R value to an L value. And you can try and build around that. I'll undo that and uncomment this here. Build and run again, and again we'll get the R value reference. Now one final note, I mentioned that I'll come back to the integer here. In module 101, I talked briefly about the fact that you can convert one type to another type, such as a float to an integer. That is also referred to casting, so casting or converting one type to another type. Again, if I go and uncomment this now, remember that we'll get that error. An R value reference cannot be bound to an L value. My int is an L value. This right here expects an R value. So it basically expects as an argument some temporary variable or some literal, in other words an R value. Okay, how can we now convert this to an R value or a temporary? Well, we can go and cast that. This line here is going to convert that basically to a temporary now. Okay, and this works fine now. Maybe one final example. I'll set this integer here to be also an R value reference. And again we'll get an error. Okay, so this works fine. This is going to calculate and the result is going to get stored in some register, right? It's just a temporary. And we can assign some temporary to an R value reference as we are doing right here. And then we are trying to pass that in here to this function. And you might expect that to work because you can say, okay, well, the type here matches this type. Well, you have to think about, again, the difference between the type of the variable and the category. So again, this might be an R value reference. The type of my int might be an R value reference, but it also has a category of an L value. This is also an L value itself. So here where I use it, this is an L value. Again, to get that to work, again, I convert that to a temporary and I'll just print that out to see if it passes in properly, and you can see we get 110 printed out and R value reference. Okay, so just a recap on some of these basics. The move constructor as a formal parameter does not have an L value reference like this right here, right? The move constructor will actually have an R value reference like here. And that is what brings me to what the move constructor prototype looks like. In the first point, in that first example, you can see what we have covered previously, which is the copy constructor, and then also the move constructor. The move constructor has, as a formal parameter, an R value reference, whereas the copy constructor simply has an L value reference. Okay, let's look at a simple example in Visual Studio where we do not have a pointer member, just to get an idea for when the move constructor will get invoked. And then we'll move on to a more complicated example where we actually do have a member pointer. For this example, I'll be using our handy entity class again. In the private section, I have an integer called a member. Alright, so the constructor here is going to simply print out default constructor invoked. Again, it has this default argument here set to 1. And then here is the copy constructor. And all these constructors are gonna do, since we do not have pointers, is just going to do other.member, alright, it's going to fetch that and assign it to the member of the calling object. Alright, then this copy constructor will print out copy constructor invoked. Here is the move constructor, and you can see the difference again in the headers for these constructors. the move constructor will also print out move constructor invoked. And then I simply have this function right here again. I overload the addition operator. I talked about return value optimization in a previous lecture, so I'm doing this here purposefully so that we do get that temporary constructed. Otherwise it may not construct that temporary and then we will not see any output. And I can actually do it in that way. Yeah, that's fine. Then I simply do toString, which will print out the member here. Then in main, I construct entity 1 and 2. I pass in 3 as an argument for both of those. And then here I construct another entity, entity 3, and I construct that with what I return here from this assignment operator. That is going to return a temporary object, and instead of using the copy constructor here, it should use the move constructor instead. And then I simply do entity 3.toString, build and run that. So get default constructor invoked a couple of times, and then move constructor invoked, and then it prints out 6. Okay, so you can see we use the move constructor instead of the copy constructor. So remember what we are going to get here is a temporary. It's going to invoke that function right here. Within the body of this overloaded addition operator, we create this entity, this temp entity, and we use this integer here to initialize that, and then we simply return temp. This is also what some people get confused. This function is not going to return this particular object, temp. When this function terminates, right, or returns, this local variable, temp, is going to get destroyed. But it will store, in this case, a temporary object somewhere in the memory. It's not named or anything, it's just some temporary object. Alright, so let's scroll down now. That temporary object is now in memory somewhere in some register. Okay, it's kind of floating around. Let's say we replace this now with that temporary object. Now we want to construct this entity 3 as a copy of that temporary object. In previous lectures we've seen that that would now use the copy constructor, but sometimes the copy constructor is not as efficient as the move constructor. As we'll see later, we'll move stuff around. In this example it doesn't really matter which one you use. Again, I just want to show you where this gets invoked, and the reason why it uses the move constructor is again because the move constructor takes in an R value. And of course that temporary object that this function here returns will be an R value. Okay, now I can actually comment this here out, and then it should call this function right here with the copy constructor. And as you can see, that works, so copy constructor invoked. I'll undo that and I'll scroll down to over here. Now if I do this and I build and run, you'll notice that we have one less construction, and that again has to do with the return value optimization. Okay, the next example is going to be based on the entity class again, but in this case we have the deep constructor because we will have a member pointer. You can see we have member pointer. This is a pointer to an integer. Alright, we'll also be using the overloaded addition operator. Okay, so I'll be constructing a temporary object, and in this case, because it's a pointer, I'll have to dereference this member pointer to fetch the value, and then do addition, and then fetch the value again from the other member pointer by dereferencing it. In the destructor, again, we'll talk about this in a bit more detail here in just a second, and the same with the move constructor. Okay, but before I talk about the definition of this class and the move constructor and so on in a bit more detail, I'd like to step you through another illustration which may make this easier for you to understand and to follow. Okay, so here's an illustration that I'll walk you through on the move constructor with a pointer member. In the top left, we have an example of a move constructor for an entity class. The formal parameter is an R value reference. Let's move to the main function. You can see I have two entities here, entity 1 and entity 2. I pass in 3 again as an argument to both of those, just like we've done in the previous subsection. Now for this illustration, we will not have entity 1 and entity 2 on the stack. We are going to focus primarily on entity 3 and then also the temporary object. So of course I'm not going to step through all of the lines here, that would take too long. So we are going to focus where we initialize entity 3 using that temp object. Okay, so this is where we are at currently in the program. We are at the second statement in main. We construct the object entity3, and that is going to get initialized to some temporary object or an R value. And the reason is because we do entity1 plus entity2 between parentheses, and of course that's going to use the overloaded addition operator that's going to get called on entity1, and we are going to pass in entity2 as an argument to that. It's going to do that calculation and it's going to return by value as we've seen before. And because it returns by value, we get a temporary object created somewhere in memory, in other words an R value, and we now are trying to initialize entity3 to that temporary object. Okay, so let's look at what we have on the stack and on the heap. We have that temporary object which is about to be destroyed, and just like your other entity objects, that will have some member pointer that points to some object on the heap. For this example, the dynamic variable on the heap is just an integer, okay, just to keep it simple. But just like with our previous examples, this could be an object, this could be an array of integers or floats, or even an array of objects. Okay, so in many of those cases it's more efficient to move things around instead of doing a sort of deep copy where I'll have to create new dynamic variables on the heap, copy things over, and stuff like that. And of course that's going to be a waste of time because the temporary object is going to get destroyed anyway. Okay, so I have that temporary object on the stack now, and now let's see what happens in the move constructor. You could do the assignment in the body, but I'm using the initialization list here, just like in the other constructors. So in the initialization list I do member pointer, so I assign other.member pointer to the member pointer of the calling object or the object that we are constructing, in this case entity3. And again, we are not referencing those, we are not copying the values over, we are copying the address from the temporary object, right? We are assigning that address to the member pointer of the object that we are constructing here, in this case entity3. So of course that means that both the temporary object and the new object that we are now constructing will both point to the same dynamic variable on the heap. That brings me to that statement that's in the move constructor, other.memberPointer. Okay, we assign null pointer to other.memberPointer. This is a very important step because remember now, following that statement where we construct entity3, that temporary object is gonna get destroyed. And as with all of the other entity objects, when that temporary object gets destroyed, it's gonna call the destructor, which is going to deallocate whatever the member pointer is going to point at. Now if that happens, if you should go and deallocate the dynamic variable pointed to by that member pointer, okay, the member pointer of temp, the member pointer of entity3 would now be dangling, and when we go and terminate the program or destroy that entity3 object and its destructor gets called, again it's going to try and deallocate whatever member pointer of entity3 is pointing at, and that will again cause a crash. And to avoid that, you assign null pointer to other.memberPointer, of course other in this case being the temporary object. And as you can see from the illustrations on the stack and the heap now, the member pointer of the temporary object is no longer pointing to that dynamic variable on the heap, and it's also not dangling, it's simply set to null pointer, and basically the resources of the temporary object has now been stolen by the entity3 object. In other words, the resources of the temporary object has been reallocated to the entity3 object. Following that second statement in the main function, so following the construction of entity3, that temporary object is gonna get destroyed. If it calls its destructor, it doesn't really have anything to deallocate. So there's no problem with that, and we even reduce some of that computation that may be involved with that. Okay, so I hope this illustration helps you visualize how this move constructor works and how we can reallocate resources from a temporary object or an R value to an L value. Okay, let's look at this example in Visual Studio now. I have the entity class again. Here I have the constructor. This is going to assign a new dynamic variable on the heap. Okay, a new integer, and it's going to assign that to member pointer. Okay, member pointer here is a pointer, right? Alright, then we have the deep copy constructor right here that is going to delegate that construction to here, to the default constructor. Okay, as we talked about before, and it simply prints this out as well, copy constructor invoked. Okay, so here is where we want to get at, the move constructor. You can see the difference here in the headers for these two. The copy constructor again has an L value reference, a reference to an entity constant, whereas the move constructor has an R value reference to an entity. Now that's only an R value reference to entity and not an R value reference to entity constant in this particular example, because of course in the body here we want to do this assignment. Okay, we want to assign null pointer to other.memberPointer. Other again is going to be whatever we pass in this case an R value or the temporary object. Alright, it prints out move constructor invoked, and here is the initialization list. Okay, we are going to copy the address or assign the address, right? So we do other.memberPointer, we assign that to the member pointer of the calling object or the object that we are constructing. Then I have a destructor right here as well. Now you can do some checks in here if you want. I mentioned previously deleting a null pointer doesn't do anything. Okay, you're not going to get a crash, but it may be a good idea to do a check for that anyway. So I do a check for that. If member pointer is not null pointer, then go and deallocate whatever member pointer is pointing at and print this out, dynamic object deallocated. Otherwise, simply print out nothing to deallocate. Alright, in this case, member pointer will be null pointer. You need to make some changes to this by dereferencing member pointer and then doing the addition operator, and then do other.memberPointer and dereference that to fetch the actual values that are stored in the dynamic variables that these member pointers are pointing at. Those will return integers. You add those together and the constructor does take in an integer, right? So you return that temporary variable. Basically that's going to create a temporary object in memory somewhere, and when this function returns, the local variable will actually get destroyed. And I have this toString function right here as well, which will simply dereference member pointer again to print it out. Okay, main is basically the same as in the previous subsection. I construct entity 1 and 2, both by passing in an argument of 3. Then I construct entity 3 right here, and then between these parentheses I pass in entity 1 plus entity 2. Okay, and that is what is going to invoke that overloaded addition operator, which will create a temporary entity object, which we are then going to use to initialize entity 3. And then I simply do entity 3.toString. I'll just build and run this, and this should print out 6 just fine. Okay, so let's look at this output here. The move constructor gets invoked. It prints out nothing to deallocate because we do that assignment. So we set other.memberPointer, alright. We assign null pointer to that. It prints out 6. Right after this final statement here where I do here end of program, of course it reaches the closing curly bracket of the main function right following this end of program printout that it does. Then it's going to go and destroy here entity 1, entity 2 and entity 3. Okay, and so it's going to deallocate the dynamic objects that the member pointers of those objects are pointing at. Okay, so before I close this down, in just a second I'm gonna comment out the move constructor. So I'd like you to take a note of this output here. The final line should be pretty much the same, so end of program and then dynamic object deallocated 3 times. But then at the top we should get copy construct invoked instead, and then also dynamic object deallocated instead of nothing to deallocate right here. And it should then also still print out 6. So I'll comment out the move constructor, build and run again, and that is exactly what we get. Copy constructor invoked instead of move constructor invoked. Dynamic object deallocated. Remember previously we did not have to go and deallocate this dynamic object, and it still prints out 6, and the rest is still the same. Okay, so I spent quite some time trying to illustrate this to you, and I hope it's clear how we sort of reallocate resources from a temporary object or an R value to an L value. Alright, so I hope you found this interesting. Now there is one final thing I'd like to note. I'll just go and uncomment this here. If you go and try this by yourself, you may notice a green squiggly may appear under entity, and what you want to do is you may want to go and add this keyword right here, no except. So I've sort of avoided that no except specifier so far in this video, and we can see that it works without it, and it's not really a warning, so it won't give you necessarily a warning when you compile. It's just the Visual Studio IntelliSense trying to help you out. Now the no except specifier defines a function to be a non-exception throwing function. This means the implementation should be reliable and handle possible error conditions. Now with the move constructor and the move assignment operator, it's a good idea to add this, but we'll talk about exceptions in more detail in a future lesson. If we go and build around this, you'll see this still works fine. Move constructor invoked, nothing to deallocate, and so on. Finally, I'd like to note that in some instances, because of the optimization that the compiler does, such as the return value optimization that we talked about previously, you may not always get the printouts. Okay, so sometimes some of these constructors may not even get invoked in the way that you would expect. Okay, and that again is why I have the addition operator overloaded in this way. Okay, where I have these statements like this in the body. Okay, as I explained in the previous subsection. So when you're playing around with copy constructors and move constructors, and you are doing printouts and you're trying to understand what's going on, then remember that return value optimization. Try and avoid that by doing what I've done here. But then, of course, in your final code, you want to actually construct the object in the return statement, okay? Because that is again another optimization, which may reduce even more temporary objects. Okay, just one final example for you, something that I kind of forgot to mention in the previous section. Here we have the move constructor. Now I mentioned this right here where we assign null pointer to other.member pointer. This is a vital step. So if I comment that out now, it's not going to set that to null pointer, and that temporary object is now going to get destroyed right following this here. Right following this statement, that temporary object is going to get destroyed by calling the destructor. It's going to deallocate the dynamic variable that the member pointer of that temporary object is pointing at. But remember now that the member pointer of entity 3 is also pointing at that dynamic variable. So in other words, following this statement, the member pointer of entity 3 will now be dangling. Okay, and that's going to be really bad. We may get crashes and undefined behavior. Okay, so I'll just build and run this to demonstrate it to you. All sorts of wrong here. Okay, abort. You can see what happens here. Move constructor invoked, and then you destroy or deallocate that dynamic object. Okay, you don't want to do that. That is why in the printout we get something weird, some garbage printed out, and the program simply crashes. So always remember this step right here with the move constructor. Okay, I hope you understand this move constructor now. I hope you found this interesting, and I'll see you in the next video.